So I'm going to talk about uniform color scales, the Optical Society of America uniform color scales, color space, which was developed in the 60s and has been sort of in the back of my mind as a pretty interesting structure to use in cartography. I'm going to apply it in this talk, apply it to designing bivariate sequential color schemes on thematic maps, which is pretty narrow, but I'm hoping you'll see the general use of it. I'll talk about color schemes real quickly, just to get us all on the same page there, and then talk about the structure of the OSA system, and then do 3 examples in ArcGIS Pro. So I designed Color Brewer 20 years ago, more than 20 years ago. I did bring a present for you. I found in my office a big box of reprints. Back in the old days, when you published an article, and this was published in 2003 on Color Brewer, you could buy reprints, and so because it had the color in it, I did buy a big box of reprints. So there's a big stack there. So please take them if you're interested in them, because it's a physical version of what you see online. So I designed Color Brewer way back when, and that's the one screen of it. Those color schemes are now in ArcGIS Pro, and I think some of the more valuable of them are the sequential schemes that run from. Should I do something different? Okay. Through light to dark, but through multiple hues. And so essentially what I'm doing when I design those is going from light saturated around color space, keeping saturated through multiple hues down to a dark color. So I'm doing something geometric in that space. I tend, for perceptual space, think in Munsell coordinates. And you probably are familiar with Munsell from some part of your life. So it's a system with cylindrical coordinates that has a hue, value, and chroma set of axes. So I was acting out there that yellow, green, blue scheme. The Optical Society of America and uniform color scales. The uniform means there's equal perceptual differences between equally spaced colors. And that's a little harder to do in Munsell because everything converges to that center neutral axis. So when you have different hues around the neutral axis, they're barely different as opposed to as you get further out in the cylindrical coordinates. And the system is built as a cuboctahedral lattice that you can take cleavage planes through. So that's like, oh, what does that mean? and actually creating this talk helped me better understand what it was. I had a vague idea. So I'm going to try to walk you through what that means. But first, some reminders of bivariate mapping. In the Census Bureau did a whole set of these in the 70s for urban atlases, and Judy Olson, my advisor, was a key advisor on that design setup. So this is education and income by county for the US. So you understand how the 2 variables interact. That's the emphasis. Here's a recent one from COVID, published in the Washington Post, and it's vaccinations and hospitalizations. Here's one from the physical sciences from about 10 years ago, which is carbon storage and surface temperature, and where they're both high. So these are been in the literature and more so as people have better tools for making them. Judy and I structured the relationships between types of color schemes, qualitative, diverging, and sequential. I'm not going to go through this in detail, but I'm to put it up, so say we're down in this corner where we're combining 2 sequential schemes. Two data sets where you're emphasizing low to high, and their combinations. I talk about it a little bit in my book, Designing Better Maps, and so here's one of the sequential schemes and then a combination, in this case, crime and vacant lots. I don't know what's going on out there. I think it's wind. So that's a quick version of bivariate schemes, sequential. So when I design one of these, what I'm doing is this is just the high on both. I'm going to turn this axis, XY axis, to the diamond-shaped option, and that's somewhat inspired by John Nelson's, this is 2016, but I thought that was pretty effective, putting the high at the top of the diamond and down to the bottom. It also mimics a little better how color space is structured, though the light's on the bottom and the dark is on the top. So I'm going to really confuse you by flipping over the color space as we go, but just a shout out to John. And I've seen more, we've all seen more maps with this diamond layout over the years. So, light to dark and going towards two hues. This is, when I design these, I'm really trying to get dark. Can you see my cursor? No, I can't see it on my screen, but dark at the top, equal lightness across that angle down to light, and smooth transitions all the way. So on this one, which is a really easy one, is you can focus on the cyan component, you can focus on the magenta component, or the combination. And so you're emphasizing one hue here, one hue there, and the combination of the hues. So that's the basics of designing those. But I'm doing it typically with CMYK numbers or RGB numbers and looking at each scheme and critiquing myself, what am I got equal lightness, and so forth. But if you want to do something more complicated that's just not cyan magenta, because you don't want every map to be cyan and magenta, it's a little harder. So this is Aaron's map, where he's really got different hues, but he's still got that light, medium, dark sequence going up the vertical. So how can we make these? So now I'm going to switch over to trying to describe the cuboctahedral to you. So here's one cleavage plane with, before that description, out of the cuboctahedron, and I put a diamond shape on it and circled a few colors to give you a sense that this is pretty varied color there, but even transitions, equal perceptual spacing. So maybe we can plop into that, grab a set of colors in this geometry, and come up, bang, with a bivariate scheme, which would be pretty cool. So we talked about Munsell being cylindrical coordinates, the Optical Society of America, uniform color scales. I pulled this lattice from engineering. They were talking about stress pressure and how it breaks as you push on it. So it's being used in other environments. It's an opponent color space, and I'll explain that first. And so the opponent colors are red, green, and when you have opponent color spaces, they tend to be kind of a orangey red and a tealish green. It's not the green I think of. And then the other axis is a yellow to blue. OSA uses a J for the yellow because Y is a sort of a key, has a key meaning in color science with XYZ spaces. So they use a J for yellow, a G for green, and then an L for lightness. So it's L, yellow, green, yellow, blue, green, red, opponent space. And I put the Munsell space back there, not that it's the same space, but to remind you that this isn't some symmetrical cube of color. It's a blobby thing that's higher in the yellows and lower in the blues, and it's an irregular shaped color solid. What's a cuboctahedron? Well, take this apart. It's a cube. Take a cube, lop all the corners off it. That's the octo. Cut all the 8 corners off it, and it's a polyhedron. Apparently, it's an Archimedes solid, which I don't know anything about. But what that buys you is every vertex is an equal space from the center. There's 12 vertices in there that are all equally distant from the center. That's way better than just, well, whatever, 4 or 6. So it's got triangular faces and square faces, but you can stack it into a lattice and do those slices through it. So here working from this diagram, which had a few errors in it, but it's on a good site, I redrew this. So there's my cuboctahedral. It's a little tilted because that's useful. And the coordinates on each of the corners. So you see them as 1, 1, -1, or 0, 0, 2. And I've got the green, red coming this way toward us, and I've got the yellow, blue going that way, horizontal, and light to dark on the vertical. So and if we slice this up, so this fella I have a credit to his name earlier in the slide, but this fellow has all the cleavage planes through this space, and you define them by relating, like this is a real simple one, that all the j equals some number, j equals 0, j equals 1, j equals 2. So you're going parallel with the yellow-blue axis, marching through color space. You can see that doesn't look like yellow-blue axes, right? There's all kinds of colors in each of those slices. And you can see the irregular shape of color space as you march through it. And some of them are quite, the positive high numbers there, there's like only 2 colors on them, those dark colors are down low. But there's lots of exciting combinations on those cleavage planes. So here's a G equals 0, so we're coming right through the middle of the cuboctahedron. And so see the numbers I circled there? See the last number, the little triplets, 0, 2, 0. The way you define this is that you always have 0 there, right? 0, 0, or G equals 4, for example. So you slice that. Here's slices at -2, 0, and +2. You can see the colors change through there. So you're going blue, yellow, adding some green, adding some red as you move through that lattice. And there's 6 directions for these slices. Here's an example of just lightness slices. So you've got the yellow, blue, green, red. Here's a more complicated one. So this is J minus G equals a certain number, in this case 2, or 3, or 4, so forth. So that's at a diagonal to both axes, yellow, blue, and red, green. So here's J minus G equals 2. Over on the other side is J minus G equals -2. So you're slicing at an angle all the way through there. So I'll keep going there. So that's that lower scheme there, zoomed up. So you can see pulling a nice diverging scheme out of there, arcing from the purples up to the top and down again. Here's the L plus J, so that's more of a high angle coming down through. So the L, 1 plus 1 equals 2, but 0 plus 2 also equals 2. So that's how you define that axis. So here's 3 slicing down through. Here's 3 example slices. These ones look a little more similar. So they go red, green, and then they're bluish towards the top and more yellowish towards the bottom. It's that set out of the cleavage. That's that set out of the cleavage planes. So here, let's put a sequential scheme on it. I've got the high here, the low here, the high low for the high on one variable, low on the other. The RGBs are just there for how I made this map in Arc Pro, right? So I put each of those colors from this cleavage plane into the spots in the bivariate legend, and this happens to be percent, it's the ACS data for percent in households with no computer and percents with a BA or higher degree with no computer. So that looks like a real scheme. It's doing its lightness thing. It's got a pretty good variety of hues on there. Here's another axis, the L minus G, so we're coming down, we're having planes slicing downward through that lattice. Here's 2 examples. So they go from, in this case, blue to yellow. And at the top are greenish, at the bottom they're reddish. You're gradually adding more red, gradually adding more green as you move up. But also doing light to dark. That's the hard part. Add to the 2 hue aspects and go light to dark. So here's the upper one there, bigger. And I'm doing this seat of the pants. I'm just doing, okay, I'm putting a circle through there, but keeping it within all the colors and then grabbing colors at the far edges so I get a good hue saturation and hue variety. and then picking one that's nearby. So I'm not programming this. I'm doing eyedropper off the graphic. So, but that's what that scheme looks like. I think that came out actually quite nice. It's going light green at the bottom to a dark brownish purple thing, and then over to I don't even know how to describe that. And that's the beauty of this, I think. It's a color you're not really usually seeing, sort of a orangey greeny thing, and then over to a blue, and it's lightness stepping upward. This one is no computer at home and less than high school degree with no computer at home. And then another axis plopping this into the 9 colors into the space. This one didn't work out as well because I'm a little crunched at the top. I don't think I picked the right things at the top. But that's a scheme. I think this one's too dark. I fiddled with it, but I didn't keep fiddling with it. So you edit these in ARC. If you're in ArcGIS Pro, you do the drop down. There's a format, the color scheme. It brings up this tool. You can rotate it and set each color. So if I click on that color, I can change the RGB or other spec on it. So I did 3 of these for you through 3 cleavage planes, and got those 3 color schemes. So I think it has potential as a automatic, potentially if you program the coordinate system, way to come up with a really wide variety of bivariate color schemes. But I haven't done that yet. And OSA-UCS is a kind of old space from the 60s, so it's a little bit fugitive. I'm not finding as many code pieces on it, but I haven't looked super hard. But don't despair. There are lots of bivariate schemes in ArcGIS Pro. These are the ones that are already built in there. If you can click to show names, that's often helpful. And some of these are mine, and some of them are other designers. And if there's, Craig, I don't know if you know who at Esri is doing the bivariate designs. If there's someone at Esri here that knows who did the designs, they did a good job. So anyway, that's all. Questions? One? Yeah, I guess you would just do put a 3D map a 3D space into that lattice, and you'd come up with trivariate. Trivariates are tricky because if you have to have to get it on a flat page into a triangular scheme, you have to have all the variables add to 1, which makes it a little hard. But certainly there's potential there. There's potential for any of the bivariate schemes. You could drape them differently in the space. I just did flat planes because that suits the sequential. Oh, yeah, it's a continuous space. I just had examples from other designers who did it at integer values. But yeah, it's a continuous space with equal perceptual spacing in all directions from all colors. Pick a color. Any color in there has 12 equal spaced neighbors, which is really different than any of the other spaces. And it'll run out. You hit the edge of the gamut on what your equipment can show or what you can see, but it's equally spaced throughout the whole thing, which is, I think, a really cool characteristic for that space. Thanks for the questions. And do come up and grab a Munsell paper if you are interested.